All right, so right now, after discussing the find difference method, we are moving to more popular discretization methods, and I think find volume is probably the most popular discretization method in CFD, although finite elements are also used that we'll cover later. Like during the break, we had some discussions with Konrad regarding the generalization of the find difference method to more complex geometries. Like we stated that yes, this can be done. You can probably even derive the formulation of stencils for stencils that are not that where the angle is not 90 degrees. But it causes so many difficulties that yes, it can be done, but probably there are better methods to do the same. And I think the find volume method is one of the better methods to do the same. However, find volume method has got its own disadvantages as well, and I think we will cover some of them. Anyway, let me start with the formulation for the scalar transport equation. I need to move the cable. All right, so finite volume method. Again, it's a method to discretize partial differential equation. And let's start with the general scalar transport equation plus divergence of velocity times the scalar quantity equals divergence of the diffusivity times the gradient scalar quantity plus the source term. I need to do one more thing, just a minute. And as in the find difference method, we've been starting with the differential equation. In find volume discretization, we want to move from the differential equation to basically the integral equation because we want to express the balances between some volumes. And what I mean by saying this is, well, if you've got any domain in which you want to solve your PDE, the find volume method assumes that you do some space subdivision not a very nice one. But let it be. So whatever the domain you have, is you subdivide it into find volumes. And we will be writing integrals over just one find volume. So we are starting with that, but right now we are integrating the equation. Omega, and it's not omega of the whole domain, it's omega v. Let me denote omega v as the subdomain of one find volume. So basically this one is omega v. Okay. And the integral of the omega v again. Or even minus omega v divergence of lambda times gradient of u d omega plus omega v, the source term, times d omega. And now we are coming to the assumptions of the finite volume method. First, the assumption of a finite volume method is that if you select any finite volume, let it be triangular or completely general finite volume, the first assumption is that you average the quantity across the whole finite volume. So first of all, the assumption is that we can represent, for example, this one is based on the mean value theorem, that we can represent it by some average value times volume of one finite volume. Okay? So to say, finite volumes assume that across the whole finite volume you've got just one value. So if we apply this assumption to the first term, we end up with d dt u average times v. Okay? If we've got constant mesh, and let's assume for a minute that we've got constant mesh that doesn't move, then obviously the volume is all the time the same. The only thing that can change is the value of u inside the finite volume. Mm-hmm.
So didn't we call the volume omega v before?
If you wish, we can write it like that. But I would prefer writing simply v. We can define that integral over omega v d omega is by definition. Okay, we can even write like that. That's the first assumption. Some notions. Generally, there are two types of defined volume method. Let me start with one of them without explaining the other one right now. We will be focusing on the cell-centered volume method. Cell-centered finite volume method, which assumes that we are representing all these average quantities at the centroids of the cells. So what it is, it's nothing else as the centroid. And centroid is defined if you calculate the center of mass of such a volume or area, then centroid is located exactly at the center of mass of such a volume. Okay? Okay, so to say, we have already discretized the source term. We have discretized the first term. And what we want to do here is we want to apply the, it's equal sign. What we want to do here is we again want to apply the Gaussian theorem to replace the volume integrals by the boundary integrals. So let me do that with the first term. And this term can be translated into the gamma v. Again, will be not the boundary of the domain, it will be the boundary of a specific finite volume. And then the unit normal vector times velocity times u d gamma. And again, if we apply the Gaussian theorem for this one, then we see that the integral can be expressed by saying that it's the boundary integral of unit normal vector times lambda times gradient of u d gamma. And let me rewrite that. Okay, let me rewrite it here. Or maybe not, because I'm not going to mix the discretized version with the non-discretized version. So let me write this one. du dt omega v d omega. Then this one translates to that. Plus or minus equals omega v f times d omega. And this is the first difference. Like, as we've been discussing the find difference method always starts with the strong formulation of the differential equation. What the find m method, what the find volume method is using is it translates the differential equation into the integral equation, and just something that we want to discretize is this integral equation for the fluxes. First of all, what you can see is this one is the convective flux. This one is the diffusion flux. Again, source term and the time derivative. So the find volume method will be working with very deeply. We'll be working with the convective fluxes and the diffusion fluxes, and flux is something that is particularly associated to the find volume method.